Today we are going to talk about exponential functions and their models. So we will be looking at what is an exponential function, what does the graph look like, and where are some real life situations where we see exponential models. So first of all, by definition, an exponential function is a function in the form of f of x equals a b to the x, where a is the initial amount and b will be the rate of growth or decay. Exponential functions will always form a J-curve. So I have one here, y equals 2 to the x, where a is 1, b is 2, and the exponent is x. This shows exponential growth since the rate of growth is greater than 0. It's 2. So in this case, our function is doubling. In exponential growth, there's always an asymptote of y equals 0, which is right here. So the curve will never hit that asymptote. When I use this parent function of y equals 2 to the x, I pick values. When I put negative 1 in there, I get 1/2. When I put 0 in for x, I get 1. When I put 2 in for x, I get 4. When I put 1 in for x, I get 2. So I just plotted those points, negative 1, 1/2, 0, 1, 1, 2, and 2, 4, and drew my J-curve through it. Notice that exponential models will occur for each unit of x. The y values will be multiplied by a constant of b. A is the y value when x is 0. So in this case, right here, a is 1. Whereas before, we studied linear functions. And here I have the parent function y equals 2x. And notice it makes a straight line. Linear models do not grow as quickly as exponential ones. Instead, they grow constantly, where exponential grow multiply. Remember, with linear models, you find the slope by taking your change of y's over your change of x's, and that should be consistent and constant. So let's take a look at a few examples where we're just given data and we have to determine if it's exponential or linear. Okay, first of all, we're given the table where x is 0, 1, 2, 3, and 4, and y is 1.5, 3, 6, 12, and 24, respectively. So if we're going to test if it's linear, we want to do the slopes. If we're going to test exponential, we want to see how y2 compares to y1. So let's test the slopes first. So slopes is change in y's. So this change is 1.5. From 3 to 6 is 3. From 6 to 12 is 6. 12 to 24 is 12. Over x's, 1, 1, 1, and 1. So when we compare that, we have 1.5 over 1, 3 over 1, 6 over 1, and 12 over 1. Are these slopes constant? No, they are not equal. They change every time. So we know it is not linear. So to test exponential, let's just take our second y value over our initial y value. So in this case, I would have 3 over 1.5. 6 over 3, 12 over 6, and 24 over 12. Are those constant? Yes, they all reduce to 2 over 1. So I know it is exponential. So that 2 then becomes our b value. And our a value happens where x was 0. So that occurs right here. So it is 1.5. So when I plug it into the equation, y equals ab to the x. A was 1.5, b was 2, raised to the x. Over here, we have another table. 0, 1, 2, 3, 4 for my x values. 3, 4.5, 6, 7.5, and 9 for my y values. So again, I'm going to do 2 tests. I'm going to do a linear and an exponential. So let's check the linear. Change in y over change in x. Oops. This change is 1.5. 1.5. 1.5. 1.5. Change in x, 1, 1, 1, 1. So every time I have 1.5 over 1. Is that constant? Yes. I have a slope of 1.5. So it is a linear equation. I shouldn't even have to check exponential then. So linear is y equals mx plus b. My slope was 1.5. B is where x is 0. So it is 3. So my equation is linear 1.5x plus 3. So far we've looked at 2 numerical representations. Now let's look at a graphical representation. Just by this graph, does it make a line or a J-curve? It makes a J-curve, so this will be exponential. So exponential, I need to find A and B. Because y equals AB to the x. So I'm just going to take my points. I have 1, 2, and I have 2, 8. And remember, when we test exponential, we take our y2s over our y1s. So y2 is 8 over y1 is 2. So 8 over 2 is 4. So my constant growth is quadrupling. So that is 4 to the x. But I don't have 8. So I can just, I don't have A. So I can just stick in this point y is 8 equals A I'm looking for. 4 to the x is 2. So this becomes 8 equals A times 16. Divide by 16. And A is 1/2. So my equation is y equals A 1/2 times B 4 to the x. Now let's look at some authentic situations. First of all, when you get a job, your salary is $40,000 for the first year. The second year, it's $43,000. In the third year, you earn $46,000, and so on, and so on, and so on. So I like to draw myself a picture. In the first year, I earned $40,000. In the second year, I earned $43,000. In the third year, I earned $46,000. Etc., etc., etc. Now, I told you it was a linear model, but can you tell me how I know it's a linear model? These would be my y's, and these would be my x's, because it would be dollars earned per year. So the change in my y's is 3,000 over the change in my x's is 1. So my slope is 3,000 over 1, or $3,000 per year. So when I put it in my model, y equals m 3,000. And since I don't have year 0, I have to do x minus 1 plus b. So x minus 1 plus b, if I go back 3,000, I'd be at 37,000. So if I figure that out, I'd have 3,000 x minus just a minute here once. If I'm going to figure out b, it would just be x. So it would be 3,000 x plus 37,000. Since I didn't have year 0, I had year 1. That's how come I put in the 1. And I would get to the same place. 3,000 x minus 1, and at 1, I had 40,000, which gives me 3,000 x minus 3,000 plus 40,000, which is my 3,000 x plus 37,000. So you can either count back your slope, or you can stick in your point that you have, and you get the same equation. Now let's look at the same salary situation. I still start with $40,000, but each year after that I receive a 5% raise. So the first year I have $40,000. The second year I receive a 5% raise. So to get my 5%, I have to multiply by 1.05. So if I multiply 40,000 by 1.05, we get $42,000. And in the third year, I have to multiply by 1.05. I get 44,100. In the fourth year, multiply by 1.05, etc., etc., etc. So this would be an exponential model because I am multiplying to get my next term. So exponential, y equals ab to the x, but again, I don't have year 0, I have year 1, so that's how come I have to put minus 1. So y equals a is my initial amount, which I don't have, b is 40,000, or excuse me, b is my rate of growth, 1.05, to the x minus 1. So in this case, when I do look for a, my initial amount was at 1, so that would be 40,000. Now, here are some symbolic ways exponential functions can be used. If f of 0 is 5, for each unit of increase in x, the output is multiplied by 1.5. Okay, we were told it's exponential. Y equals ab to the x. Y equals a. Well, this is x, y. 0, 5. So a is my value when x is 0. So a is 5. B is my growth. I'm growing 1.5 to the x. In this case, I have negative 1/4 as a point and 1/4 as a point. Since I was told it was exponential, I know it's going to be y equals ab to the x. Since b is a ratio, I'm going to have to set these equations up as ratios. So first I'm going to substitute x in here and y in here. So I get 1/4 equals a b to the negative 1. Then I'm going to set up my other one as a ratio. Now I'm going to stick 1 in for x and 4 in for y. So I get 4 equals a b to the 4. So when I look at these equations, a and a reduce. 1/4 divided by 4 is 1/16 equals b to the negative 1 means it comes down, so 1 over b to the 5th. So 16 will equal b to the 5th. So if I 5th root 16, I get, I see I made a mistake here. X, in this case, was 1, and I put 4. So let's change that to a 1. So when I bring down that other b, I don't get b to the 5th, I get b squared. So 16 equals b squared. So to undo that, I would have to square root. So b would equal 4. Then to find a, I can either stick it into the top equation or the bottom equation. More people like the bottom because they don't have to deal with fractions. So we'll just stick it in there. 4 equals a, b is 4 to the 1. To solve for a, I divide by 4, and a equals 1. So my equation, y equals a, 1, b, 4 to the x. Okay, this time, notice I still have a J-curve, but instead of increasing quickly, it decreases quickly. So that is what we call decay. That means b will be between 0 and 1. It will be fractional rate. And I'm not growing, I would be decaying. So again, I'm using this as my parent function, y equals 1/2 to the x. So again, I stuck in negative 1, and I would get 2. When I plug in 0, I get 1. 1, I get 1/2. So negative 1, 2, 0, 1, 1, 1/2. And I get my J-curve coming down, decreasing. Still have my asymptote at y equals 0. My domain, still every one of these x's is used. I do not have a limitation on what I can plug in. And my range, y is greater than 0. still above 0. So when you have been looking at exponential functions versus last chapter polynomial functions, can you tell me what the difference between an exponential function by its equation is compared to a polynomial function? On exponential, the exponent is your variable. On polynomial, the base is your variable. So that is the main difference. To have an exponential function, your exponent is the variable, and when you had a polynomial function, your base was the variable. So, just by looking at these, can you tell me if we are growing or decaying? Remember, to find growth or decay, you would have to look at b, because that would be the rate it was changing at. So in A, f of x equals 1/3 2 to the negative x. Before we can do this, our exponents should always be positive. So f of x equals 1/3 times 1/2 to the positive x. Is that growth or decay? It would be decay, because b is 1/2, which is less than 1. How about b? Y equals 4 times 5/8 to the x. b is 5/8. Is that greater than or less than 1? Less than 1, so it is also decay. Okay, here we've already kind of done some of these models, but it's just a general equation. Y equals 1 plus r to the t. This is going to show me growth. A still is your initial amount. This time r is your percent of increase, and t is your time. I still always get 100% of whatever I invest or do, plus the percent of increase. So that is why we have 1 plus r, 100% plus my rate. And when I add, that should show growth. Now it shouldn't be any surprise, when I'm decaying, I'm actually subtracting off of that 100%. So that should show decay. The other equation you need to know about is half-life. Half-life happens when A of x equals c times 1/2 x divided by h, where c is the number of grams of the element you're decaying. Since it's a half-life, my b is 1/2, and I am raising it to the x, which is the number of years, divided by h, the number of half-lives I have. So you can still see it's still a decay problem. Initial amount, my element, half is my ratio, and the reason I have x divided by h is because of my half-lives. I have so many half-lives within a time, so I have to divide out how much time I have by that half-life. So let's try one. Radioactive strontium 90 has half-lives of about 28 years. So my half-life is 28 years. In other words, it means the element will decay half as much every 28 years. Now it says, after 50 years, what percent of the sample would remain? So I have A of x equals, I start out with 100% of the element, so 100% is 1, times my half-life of, I'm trying 50 years for every 28 years of half-life. So In that case, I get .29. So that means 29% of radioactive strontium 90 remains after 50 years. Another example of growth is when we get interest from the bank for our money. And if you can get compound interest, you are much better off. So A stands for my amount of money. P is the principal, my initial investment. My rate, I add it to my 100% of my money. My rate divided by n raised to the nt. Now some people think these are a whole bunch of formulas to memorize. But if you think about it, B, it's going to be a growth rate. So it's 1 plus r. But I don't get that rate just yearly. When I compound, I get it more times a year. But I get one rate for the year, and so I have to divide it by how many times I'm getting it. But then I get to raise it to that many times that I also am compounding my money. And another interest formula is when I compound continuously. That means 365 days a year. So the shortcut to find that is the amount of return will be your principal times E raised to the RT. So I have to explain this number E. E is called Euler's number because he's the man who discovered it. And what it means is it comes from a growth factor of 1 plus 1 over n raised to the n. So if I take 1 over 1 factorial, 1 over 2 factorial, 1 over 3 factorial, and keep adding them up, I get this number, 2.718281828. Just like you're used to pi being approximately 3.14, E is approximately 2.718. Just a new number to memorize. And on your calculator, you have an E. It is above your divide key. So we're going to practice these interests. So first of all, in 1980, about 2,180,000 U.S. workers worked at home. During the next 10 years, the number of workers working at home increased 5%. So here in 1980, this would be my initial amount. I'm increasing by 5%. So I have Y equals initial amount. Let's do 2.18 million times an increase of 5%, so that's 1 plus 0.05 for 10 years, raised to the 10. So I get 2.18 times 1.05 raised to the 10. So 2.18 I get 3.55 million workers. Say you deposit $1,500. This would be your initial amount, which they call P, but just think of it as AB to the X. So this would be A. In an account that pays 6% annual interest. So that's 6% 1 year. Find the balance after 5 years. So annually is once a year. So that's 1,500 times 1 plus 0.06 once a year for 5 years, which is 1,500 times 1.06 to the 5th, which is $2,007.34. Now semi-annually, semi means twice. So this is twice a year. So still had my initial amount of 1,500, adding to that 100%, 6%, but now I get it 2 times in the year. So I have to divide this rate by 2 because I only get half of it every time I get paid, but I also get it twice as many payments in those 5 years. So this gives me 1,500. 0.06 divided by 2 is 0.03, 1.03 to the 10th. $2,015.87. Quarterly means 4 times a year. So again, 1,500, 1 plus 0.06, 4 times a year, so I get that rate 4 times, but 4 times as often. So this gives me 1,500 times 1.06 divided by 4 is 0.015 raised to the 20th. $2,020.28. So you can see, the more times I get it a year, the more money I'm going to make on my investment. Continuously means every day of the year. So that is PERT, principal times E raised to the RT. So the principal I'm investing is $1,500. E is my number. Raised to the R, my rate is 6%, 0.06, times T, my 5 years. So this is actually 1,500 E to the 0.3. And I get $2,024.79. Okay, just a couple more problems. In this city, we have 40,000 homes. Each year, 10% of the homes disconnect their septic system. So if I'm disconnecting, would this be growth or decay? It would be decay. So y equals a 1 minus r to the t, because I'm decaying. So A, my initial amount, was 40,000 homes. 1 minus my rate of decay, 10%, 0.10. Raised to the t, 5 years. 1 minus 0.10 is 0.9 to the 5, which gives me $23,619.6 homes will be on the septic system after 5 years. Okay, I still have my parent function of y equals 2x, the blue one. Notice here, a is 2. So when a is 2, it means I'm going to double my y's. Still the same x values. So I'm just going to take these y's and double them. Double a half is 1, double 1 is 2, double 2 is 4, double 4 is 8. So then I plot these points. Negative 1, 1, 0, 2, 1, 4, 2, 8. And I have made my exponential growth happen faster. Notice this one, a is negative 2. So that means I multiply my y values of my parent function by negative 2. So 1/2 times negative 2 is negative 1. 1 times negative 2 is negative 2. 2 times negative 2 is negative 4. 4 times negative 2 is negative 8. So this time I'm going to plot negative 1, negative 1, 0, negative 2, 1, negative 4, 2, negative 8. And notice I get my curve. And it should be no surprise to you, when a is positive, my graph opens up. When a is negative, my graph opens down. So let's try these two graphs. Y equals 3 to the x. So this becomes my parent function because I have nothing else attached. So when I put in negative 1, I get 1/3. Put in 0 for x, you get 1. Put in 1 for x, you get 3. Put in 2, you get 9. So negative 1, 1/3. 0, 1. 1, 3, 2, 9. Draw your J-curve. So here your domain, x is all reals. Your range, y is still above 0. This time, my parent function, let's change this up because I have a negative exponent. 3 times 2 to the x. So my parent function is right here. Y equals 2 to the x. So again, if I put negative 1, I get 1/2. 0, 1. 1, 2, 2, 4. But this time, I have a multiplier of 3. So I have to take these y values and triple them. So 1/2 tripled is 3/2. 1 tripled is 3. 2 tripled is 6. 4 tripled is 12. So now I plot these points. Negative 1, 1.5. 0, 3. 1, 6. 2, 12. And draw my J-curve. This time, my domain is still all reals. My range, still y is greater than 0, still above 0. Now let's graph this one. Negative 2 times 1/3 to the x. So what's your parent function? 1/3 to the x. So when I put in negative 1, I get 3. 0, I get 1/3. Excuse me. 0, I get 1. 1, I get 1/3. 2, I get 1/9. My multiplier is negative 2. So we're going to take negative 2 times these y values. Negative 6, negative 2, negative 2/3, negative 2/9. And now I can plot these points. Negative 1, negative 6. 0, negative 2. 1, 1/3. 2, excuse me, 1 negative 2/3, 2 negative 2/9. So my J curve is this way. My asymptote is still y equals 0. My domain, still all reals, no numbers limited for exponents. My range this time y is below 0, less than 0. This is just knowing how to punch your graphing calculator, which I'm assuming you can do since we did that last problem with continuous interest. E to the third. Just press e raised to the third. You get approximately 20.09. E to the negative 12. You get approximately 6.14 times 10 to the negative 6, which means 6 places in front, so 5 zeros, 614. Last thing, that's it. You should be able to work on your assignment.